Okay, welcome back. This is part B of the lesson on probability generating functions. Let's now look at a binomial distribution. X follows a binomial distribution with 4 trials and a probability of 0.3. I'll create my probability distribution. I've left the probabilities in unsimplified form. If I take these to create my probability generating function, my first term doesn't have a t because the x is 0. That would be t to the power of 0. The next term is multiplied by t to the power of 1. The next term is multiplied by t to the power of 2. Then t to the power of 3. Then t to the power of 4. And I sum these 5 terms. And in this scenario, we might be asked to find a probability generating function in the form of q plus pt to the power of n. And I can observe that the relevant values are q is 0.3, p is 0.7, t is simply t, and n in this binomial is 4. And so now I can write my probability distribution function as the binomial 0.3 plus 0.7t to the power of 4. Next we'll look at a geometric distribution. If we say that x follows a geometric distribution with a probability of 1 over 4. I can set up a probability distribution. Here I'll skip one line of algebra and go straight to a factored form. Probability generating function for x of 1 over 4 times t times 1 plus 3t over 4 plus 3t over 4 squared plus ongoing. The ongoing notation indicates this is an infinite series. And here I might be required to present the probability generating function in the form of a over 1 minus r, which represents an infinite geometric series. And looking at the probability generating function as I've written it, I should recognize that the infinite series component, which I'm noting is in the brackets, has a first term of 1 and a ratio of 3t over 4. I can write that in the a over 1 minus r form as 1 over 1 minus 3t over 4. And noting that in my complete probability generating function, I need to multiply by the 1 over 4t outside of the brackets. Then I will end up with the form of 1 over 4t over 1 minus 3t over 4. And if I multiply all of the terms by 4, I end up with t over 4 minus 3t. Let me up at the top bracket my infinite series expression. Ultimately what we're working towards is the format of p times t over 1 minus q times t. Notice that our p is in this distribution, 1 over 4, and q is 3 over 4. And notice that the 1 over 4 and the 3 over 4, in place of p and q, down at the bottom before my final simplification, I have the 1 over 4 in the numerator and the 3 over 4 in the denominator. And our final scenario, we'll consider a Poisson distribution. If a variable follows a Poisson distribution with a mean value of 4. I can set up a probability distribution. From here I can create my probability generating function. And here again, I've skipped the first algebra step. Here in my expression on the right, I have multiplied each term by the appropriate t, and I've factored out e to the power of -4 from each of the terms. This is also an infinite series, and the expression in the brackets is following a Maclaurin series for e to the power of x, with x replaced with 4t, which means I can write or summarize that infinite series in brackets as e to the power of 4t. And outside of the brackets, we're multiplying by e to the power of -4, e to the power of -4 times e to the power of 4t, which simplifies to e to the power of 4 to the power of t minus 1. The general form that we're following, I'll note up at the top, it's e to the power of lambda times t minus 1. And if you're asked to follow this format, the knowledge I've described the Maclaurin series, that is a component of 9, 2, 3, 1, further pure maths 2. So that's likely beyond where you are in your math studies at this point. So I'm not sure that you would be required to fit this particular form, but if so, notice that when we factor out, we end up with, on the front, e to the power of -4, and the second term in the brackets ends up as the exponent of e. So if you can take the e to the power of -4, and keep in mind that what you'll follow with is multiplying by e to the power of that second term in the series in the brackets, you can then use exponents rules to simplify to your final probability generating function. And this completes the lesson on probability generating functions.